So, students, today we are going to complete our discussion on the cast iron, and that will bring to the end of our discussion on the iron carbon phase diagrams. We will come back to it while we will discuss about high speed steels and stainless steels. So, in the last lecture of cast iron, I am going to talk about alloyed cast iron. So, to give you a perspective of this, cast iron is an ternary alloy, by the way. It consists of iron, carbon and silicon. So, iron is the parent element, carbon and silicon are the alloying elements. Well, when we talk about alloyed cast iron, we do not discuss about the addition of carbon and silicon. We discuss about addition of other alloying elements and effect of those alloying elements on the microstructure and the properties. That you must remember. Anyway, so let me just give a recapitulation what I have done and try to clarify some points on the cast iron point of view. First of all, cast irons are alloys of iron, carbon and silicon, with the carbon concentration varying from 2.5% weight percent to about 4.2% or 4.3%. So, they are mostly hypoeutectic alloys of iron and carbon, and there are mostly 4 varieties of cast iron we discussed. First one is a white iron, in which the carbon is present as a carbide or Fe3C, and rest are like grey iron, SG iron or nodular iron and malleable iron, are basically consisting of iron phases with graphite. So, to give you an idea, this is what I showed you in the last class also. You see here, this is the nodular iron, where the graphite comes as a nodule or a kind of a structure which looks like a thrashed roof, not a sphere, that I made you very clearly understood in the last class. And you can have different matrices. This is the ferritic matrix, this is the ferrite plus piletic matrix, and this is the piletic matrix. What is the meaning of ferritic piletic matrix? Well, as you know, every graphite will be surrounded by ferrite. That is because of the carbon taken by the graphite from the nearby region. So, for that there will be ferrite, and this is what is known as bullseye structure in the ductile iron or nodular iron. But if that fraction of ferrite is substantially large, then we have to call ferrite plus piletic matrix. But if that fraction of ferrite is small, as you see in this picture here, then it is called piletic matrix. You can also have a martensitic matrix, as I told you, depends on your uses. Well, if you look at the piletic matrix, this is what I told you, very interesting things. You have a graphite, and then you have a ferrite surrounded by the graphite, and away from the graphite you will have perlites. So, this structure is known as bull's eye, because it looks like a eye of a bull, that is why. There are many discussions why does it happen, but physically this is mainly because of the carbon concentration getting depleted in the region near the graphite, and that is why it is. Now, you also have a malleable iron I discussed with you. Malleable iron can have ferritic matrix, that is what I showed. I could not show you piletic matrix in the last class. So, this time I got an image with a perlite, you can see. And as you look at it, okay, this difference in the ferritic and piletic matrix probably you are seeing same. Well, no, there are some residual contrast here, you see, and if you zoom in with the optical microscope or scanning electron microscope, you can see that. You can also create martensitic matrix depending on the requirement, as I told you in the last class also, by quenching the steel from high temperature. Now, in fully malleable iron also you can have a bullseye structure, that is thin. So, that means bullseye structure is not peculiar to the nodular iron. It can also have it can be also formed in malleable iron. That is, you see here this is the bullseye around these surrounding this graphite. But this graphite here is not a nodule, but they are deformed or not deformed, they are actually basically called tempered graphite, or they form in solid state, unlike in the nodular iron. Well, this slide which I could not show in the last class also very important. This is how actually graphite grows. Okay. So, in this nodular iron, the structure of graphite is exactly like this on the left side, what is shown as A. This is taken from the book of Professor S.P. Gupta. Now, what actually happens is that this is the needle or the lamel, this is the fleck which has rotated and forms such a cone like structure by this way. Okay. and each cone is attached over each other. It is just like that, it is like an umbrella, a stack of umbrella on above each other, but they are little bit displaced. That is what is shown here. You see here the displacement is the way two cones are arranged in such that there is a axis of the two cone varies by angle of theta, and also the stop angle is which is extended by these two sides are also, it makes between the two ends of this cone, one end of the first cone is this, the first cone is second cone. So, one end of the first cone to the other end of the second cone, they makes an angle of psi. These are the two characteristic features, and this can be varied actually depending on the growth mechanism, it can be varied. So, this is how actually these graphite nodules forms in the things. By the way, in the gray iron, this thing is open. So, what you get is this kind of structure or a cabbage like structure, but in a nodal iron what you get is basically a stack of cones attached to each other. That is what is the growth, the mode of graphite in nodal iron, and this is possible only when we add magnesium, cerium, mixed metal, and thereby removing the sulfur from the melt, because sulfur actually poisons the growth of graphite. So, by the process of removing sulfur, you can allow the graphite to follow its normal growth mechanism, and then you can get this kind of structures. Well, that is about the recapitulation of the cast iron, what I told you. Now, I am going to discuss for the next 20 minutes or so about the alloy cast irons, and as I told you, alloy cast iron means alloying elements other than these iron, carbon and silicon present. Anyway, silicon can also be added as alloying element when its concentration is more than 2%. So, basically these alloying elements are added for special purpose, okay, mostly to modify the microstructure and to arrive at very distinct properties, correct, which the normal cast iron cannot provide. So, what are the alloying elements we add? There are actually 5 alloying elements normally added. Most important ones are chromium, nickel, silicon. Silicon is obviously present, but more concentration of silicon like 5%, 10% of silicon, and then you have moly and aluminum, they can be added. First of all, what is the purpose of adding? As I told you, to modify the microstructure and properties. What are the properties we modify? First thing, we need to add these alloying elements to get good high temperature strength. Nickel and chromium does that by forming carbides, and you can also give nickel actually can improve the oxidation resistance, corrosion resistance can be improved by corrosion resistance against acidic media can be done by adding silicon more quantity, and chromium can be added to form all kinds of carbides. You know that chromium actually reacts with carbon and form different kinds of carbides like iron. Iron also form Fe3C, Fe2.C, Fe2.6C. Similarly, chromium can form different carbides, and these carbides are very hard. So, by forming these carbides, we can actually improve the wear resistance of the cast iron, because cast irons are used for a variety of applications. Okay. So, we will see. Now, there are two types of microstructure we can get. Basically, one is graphite free, just like a white iron, you do not have graphite at all, you have carbide mostly, other one is graphite. Third one is more demanding in the industry, is the mixture of these two. In fact, that is the main reason we add alloying elements into cast iron, that is the main purpose, because you see in white iron you get only iron 3C, Fe3C as a carbide, and very hard and brittle material. On the other hand, in grey and in nodular iron and malleable iron you get mostly graphite, correct. So, you cannot, if you want to have a mixture, although perlite as a matrix can have a carbide present, but I am not talking about it that. If you want to have a mixture of both graphite and the carbide in the microstructure primarily formed, then you would like to add these alloying elements, and carbides being a very hard phase will provide you the wear resistance, high temperature strength, even better many other properties. Well, so we will discuss about 3 elements. First one is chromium. Okay. Chromium is as I told you added, it can be added from 2% to about 10%, weight percentage into the iron and into the cast iron. And what does the chromium do? You know, if the chromium is added about 2 to 2.5% chromium, then actually it leads to formation of two important things. Chromium addition will lead to formation of your a carbide. There are two types of carbide forms. If the chromium is about 2 to 2.5 weight% in the cast iron, this carbide is most prominently formed. This is again iron carbide Fe3C, but some amount of iron atoms are replaced by the chromium atoms. This is what happens in a low chromium addition. But if the chromium addition is more, that if you have a high chromium addition, then what will happen? Then chromium will form other carbides, like when chromium is from 12 to 35%, huge amount of chromium is added. Then instead of this carbide, sometime this carbide also forms, or C6. This is the carbide which is normally found in the stainless steel, sensitized stainless steel, which we will discuss when we discuss stainless steel, but this is what people find. Any books like Professor Raghavan's books also you will find this. So if you have a large amount of chromium addition, then this is what is going to happen. So depending on this carbide is very hard, in fact very hard as compared to this, and so therefore if you add more chromium, you will mostly find carbides. That is another problem. Suppose in this case if you add a very low amount of chromium, you will probably get some amount of Fe3C or CrFe3C plus graphite, but here when the chromium is very large, there will be no graphite. Why? Because carbon has a so large affinity towards chromium that it will bind to chromium only, and chromium is plenty of chromium is available. So because of that large concentration of chromium, carbide will bind very easily, carbon will bind very easily to chromium and form carbides. And that is why actually if you want to have a high chromium cast iron, then you will never get any graphite, you will only get carbide. So this is like a white iron. Okay, so but you know this carbide is not as dangerous as this carbide. This can be used in the real industrial practice. Well, that is what you see in this microstructure. When you have high chromium, I have written high chromium, as you see here, you have lots of these CR3, CR23, C6 or CR iron 23 C6 carbide is present. This is the most important difference when you have a large amount of chromium present. So the matrix will be obviously gamma, because eutectic reaction if you have a high chromium will be between gamma and carbide. It will not be between liquid going to gamma plus graphite. This will not happen. Only thing will form is gamma plus Fe3C and some amount of other carbides like Cr23 C6 will form. So that is actually the effect of chromium. If you add large amount of chromium, this is going to happen. Small amount of chromium, you will form carbides which is Fe3C type plus some graphite may be present. So now let us move on to the effect of nickel. So what the nickel does? Okay, nickel as you know is a FCC structure, so this will stabilize the gamma more compared to the chromium which is a BCC crystal structure. So nickel addition stabilizes austenite, and in fact nickel addition promotes the graphite formation, correct. So that is the one effect of the nickel addition, first and foremost effect. What is the second effect of nickel addition? The temperature gap, as you have seen in the phase diagram between iron and graphite and iron and carbide, if you put them together, the temperature gap, let me show you again, otherwise you will forget. Temperature gap between these two eutectic 1153 and 1147 increases as you add nickel. So that means what? Nickel addition will make the graphitization easier, because the temperature gap, the first high temperature one is the eutectic of between liquid going to gamma plus graphite, low temperature one is basically gamma liquid going to gamma plus cementite, but the difference between these two if it increased, then predominantly the graphite and gamma as eutectic phase will form from the liquid. That is why the nickel actually is normally thought to promote the graphite formations, graphitization. Not only that, there is another important issue or aspect of nickel. So, first thing I told you, the nickel addition leads to stabilization of austenite and graphite. Second, I told you that this is mainly because of the gap of temperature of eutectic reactions will increase. Third important aspect of nickel addition is that it shifts the nose of the TTT cup. Please go back to TTT discussion, nose of the TTT cup to the right side. So, that means nickel addition will help formation of austenite or formation of martensite very easily. Why? So, martensite actually can be formed in air cooling because of the shift of nose of the TTT cup shifts to the right side. So, these are things. Now, depending on nickel addition, you can have either nickel resist or nickel hard, the two types of cast iron as you see here, nickel resist and nickel hard. What is nickel hard iron? Let us first discuss, or let us first discuss nickel resist, that is better. Nickel resist will have a large amount of nickel present, about 15 to 30% nickel, and very low concentration of chromium, maybe 1 to 2%. So, because of this, what will happen? The microstructure will have nickel resist, will have basically graphite plus graphite flakes and gamma iron. So, these are the graphite flakes, you see, these are the graphite flakes present, graphite flakes plus gamma iron, along with, because a small amount of chromium is present, some carbide will form. That is what I was telling you at the beginning. Basically modifying this, purpose of alloy cast iron is to modify the microstructure. We want both this flaky graphite plus carbide present in the same microstructure along with austenite. And here you see nickel is added so much, the austenite is stable at room temperature. Austenite even did not undergo pyrolytic transformation reaction, correct. That is the basic idea of nickel addition. So, if you have a high nickel content, and this is what is true in stainless steel also, if you have a high nickel content, the gamma will be stabilized to room temperature even, there will be no pyrolytic reaction, that is what you see. These white regions are gamma, and these flakes of graphite and these small particles, these particles are actually what? They are carbides, they are mostly carbides of Fe3C type. So, this is the microstructure which you can get, and this is known as nickel resist. Why it is known as nickel resist? That is because it resists oxidation. Why it resists oxidation? There are two reasons. One, it has carbide and gamma iron present. Second one is that this flakes of graphite is nicely distributed, that is why the oxidation resistance is high. The second category of microstructure is known as nickel hard. What is nickel hard? Nickel hard will have very low concentration of nickel, not say very low concentration, it is about 4%, 4-8% of nickel, but chromium percentage will be little higher, it can go up to 8% of chromium. And when you have large amount of chromium, what will happen? It will lead to formation of cementite, that is what you see here, okay. You have gamma and cementite, these are the cementite Fe3C, okay, all these are cementites, and this is eutectic between gamma and cementite, eutectic. So, you form white iron like microstructure, you do not have any graphite present, and this is very hard, that is why I call nickel hard, okay. So, what is the purpose of adding nickel or chromium? Purpose is that you form alloyed carbides, not only you form these Fe3C, but also you form these small particles you see here, these are actually Cr23C6 carbides, that is the basically idea. So, by changing this nickel and iron concentration, one can actually form fantastic microstructures. So, I will just go to the phase diagrams of those two binaries. Okay, let us look at iron chromium phase diagram. What will happen to chromium? As you see here, if I add chromium, gamma forms a loop, small loop, gamma is stabilized only up to 10% of chromium. When you have more than 10 or 15% of chromium, the alpha phase is stabilized. So, the chromium is basically alpha stabilizer or alpha iron stabilizer, okay. And not only that, in some cases, in fact this alpha is not stable at room temperature, it can undergo, it can form even a high chromium concentration, it can form a sigma phase. Sigma has a tetragonal structure and it is also very hard. So, if you can precipitate sigma in the microstructure, you can again increase the hardness. So, that is why we use this kind of phase diagram data to modify the microstructure. Normally, to form sigma you need about 30%, 20-25 to 30% of chromium. That only happens when you have a large amount of chromium present in the microstructure. Now, what will happen if you add nickel? Yes, you see distinct change. Here alpha forms a loop and most of the region is occupied by gamma. That is why nickel addition basically stabilizes gamma iron, and that is understandable. Nickel has a FCC structure, lattice parameter is also not very different from FCC iron or gamma iron, and therefore that is why actually it forms. But in addition to that, there are other phases which can form FeNi, Fe3Ni, FeNi3. But anyway, those phases can be bypassed by fast cooling. So, and stabilizing this gamma iron is also possible. So, this is the what is important. Now, when I am not bringing the ternary phase diagram of iron, nickel, chromium, which is the obvious thing for discussions are like this, because I am not here to give you any idea about ternary phase diagrams. So, when we discuss about ternary phase diagram, this concept we will borrow and discuss further. Okay, so that is the idea about addition of chromium and nickel. Now, we can also add silicon. In the last few minutes, I am going to tell you what will happen if you add silicon. Silicon is normally present in cast iron, about 1.5 to 2% silicon, weight percent silicon is present, but I am not talking about that. When about 5% of silicon is added, okay, cast iron with that, okay, Ci with 5% of silicon, what will happen? You know, silicon actually promotes, we know that, promotes graphitization, it forms graphites, more graphites, it does not allow formation of carbide. So, it will have more tendency to form gamma plus graphite as a eutectic phase, that is what you see here. These are the graphites, graphite nodules, and these are the gamma. Not only that, you know, silicon and this gamma can be stabilized, because here in this particular things nickel is also added quite a lot, that is why gamma is stabilized. So, you have gamma plus graphite flex present in this microstructure. But silicon addition helps you one thing, silicon actually forms of the sample or the component forms a silicate, iron silicate, FeSiO3, correct, or FeSiO4 type of structure, and this iron silicate actually protects the sample from high temperature oxidation. That is one of the reason, most important reason probably, to add silicon into the alloy cast irons, and basically it improves the oxidation resistance at high temperature. So, therefore, and I am not discussing, well, we can also discuss moly. I can tell you that in a nutshell, moly actually, moly basically what does it do? Moly forms also carbides, molybdenum carbides are present, and not only that, another idea of additional molying is to make solution strengthening of the gamma or alpha phases, that can also add strength to it. But their addition of moly is aluminum is normally not much, it is about 0.5 to 1% of the alloy addition is done. So, with this as you have understood that we can modify the microstructure using the phase diagram informations available by adding these different alloy elements like nickel, chromium, silicon, moly, aluminum, and idea is to improve their mechanical physical properties by changing the microstructure. And I told you how we can modify the microstructure, what are the properties we can improve and how we can basically get those properties, what are the phases which are involved. So, now you should go back to the book and study those things carefully and try to understand their implications if you want to really know, because in this course I cannot discuss about the different phase formation and microstructure formation in detail, but most of the informations about these are available in the books. So, that is all about the cast iron. In the next class I am going to discuss about the other solid state reaction. There are two important solid state reactions we need to discuss. One is the perireactor reaction, other one is a monoreactor reaction. And that lecture will be little shorter because those reactions are not so widely seen in the phase diagrams, but they do appear in some of the phase diagrams. So, if you are working on those alloy systems, you should have some idea how these things happens. Obviously, perireactor reaction is a solution analog of periodic reaction, similarly for monoreactor reactions. So, we will bring those discussion into this. Thank you.